Thank you to everyone who came. My name is Ria. I'm one of the peer tutors at the SSC. I work with like all of the chemistries, so you might see me there sometimes. We also are joined by Ria Goyal, who is another Ria, and I believe she also works with chemistry students at the SSC. So it's always nice to have more of us, more Rias. So yeah, we're going to be going over your exam 1 review, and hopefully, if you're in the right place, we're going to be reviewing the information for Dr. Novak's class. And yeah, so let's get started as soon as I can figure out how to move. Okay, here. So yeah, so the way we're going to split this up is we're going to talk about spectroscopy, and then after that, we're going to go into some of the details for your alcohol mechanisms and your different carbonyl mechanisms. But getting started, just looking at spectroscopy, we're going to be looking at both HNMR and CNMR. Right. So our first question is just in general, how does NMR work? So like, we have been working, like, I know that y'all have seen spectroscopy since last semester, but sometimes it is hard to remember that, okay, like, you know, like we have to actually do this process. So NMR is basically a really useful tool and used in a lot of chemistry labs. What you do is you take oftentimes a drop of whatever solution you have, and you can put it on this really, really tiny sensor that will then, or you can put it in a sample tube like shown. And what it'll do is it'll take that drop and it'll use a magnet to basically process the different different parts of that molecule. So the way it works is basically NMR uses a magnet to separate different charges, and so odd mass numbers cause nuclear spin. So that's why we'll see that we do H1 NMR and C13 NMR. We don't do C12, which is the normal carbon isotope that you're used to seeing, because we want that odd mass number. And once we have that nuclear spin, that can affect how far charge travels, right, on a magnetic field. So we're going to see that that magnetic field attracts highly positive charges. And so what we're really tracking is how positive a proton is, for example, in an HNMR. And we're looking at, based on that, we can look at different unique signals that are produced due to shielding, or as we'll see, what happens when we see surrounding electrons interact with that proton or that inside part, right? So in general, electrons surround a proton, which determines like the shielding, right? That means that if we have more electrons around that proton, if more of them are like densely like located around that proton, there's going to be more shielding. There's going to be a more neutralizing effect where all of those negative charges sort of come together and they help cancel out the charge of the nucleus, right? And then, but that's not uniform across all things. So for example, even with just our like hydrogen protons, you're going to see that there can be there's possibility for de-shielding, in which either electron withdrawing groups, such as carbonyls or haloalkyls, can help sort of pull some of those electrons away from that proton, creating this de-shielding effect where that proton is increasingly positive, allowing for it to travel further on that that magnetic spectrum. In addition, resonance structures can do something similar, because what they do is oftentimes that means that your electrons are moving around between different atoms. There's no specific place where they're always going to be dense, and so that can also create a de-shielding effect. And something to remember, as something becomes de-shielded, when you look at your traditional NMR graph, you're going to see that all of the more de-shielded protons are going to go to the left, while those that remain shielded, that are not de-shielded, they go to the right, further to that part of the axis, right? And so we've talked a bit about how NMR works, but you know, the real meat of the matter is you're going to be doing a lot of NMR problems where you're going to solve to find what a molecule is going to look like based on your NMR and like a formula, right? So the first thing that we're going to do, oftentimes, there's a really good algorithm for this. We first want to calculate the degrees of unsaturation using our empirical formula. We'll look at that formula in a second. And then after that, we want to identify functional groups, which we can do by looking at those different peaks and then seeing what boxes they fit in, right? And then finally, we can also then match signals to those peaks. So like if you can, once you start drawing things out, you can say, well, okay, like I think this peak would be located here on my molecule. So you start drawing out that molecule and you start identifying where you would see those signals. And then you also want to consider splitting. That really helps you find the neighbors. It helps you start integrating where you might have like pieces of a molecule together. And then that's 5. Put it all together, right? So just looking at that first part, we're going to look at degrees of unsaturation. So there's the formula here. You've probably seen it a lot. And yeah, so what you're going to be doing is you're going to be seeing how many hydrogens am I missing? And that should tell us how unsaturated a molecule is, or how many bonds, extra bonds a carbon has to something that is not a hydrogen, right? So each degree of unsaturation can account for an additional multiple bond or a ring structure. So for example, if you were to look at, say, benzene, benzene has 3 double bonds, right? So we've got 3 multiple extra like pi bonds, and then it's got a ring structure. So this would have 4 degrees of unsaturation, right? Versus like a normal cyclohexane would just have 1. Right. So it's a really useful tool. I like to start doing like check marks to see how many degrees of unsaturation I have accounted for as I begin to build out my molecule. It tends to help me sort of think like, oh, like maybe there's a ring here. And then it helps you sort of start looking for, oh, is there like an alkene peak? Or do I see a benzene peak, right? So that can help guide your search. And then after that, we want to identify those functional groups, right? So I really like this picture. It gives you a good idea of those boxes that I talked about, the general range in which you will find a peak. By the way, I'm currently looking at HNMRs. We'll briefly look at like CNMR spectrums as well. But I do think HNMR tends to be a little more tidy and just like a little easier to think about at first. So in general, for example, when you're looking at alkanes, you're going to be looking between 0 and 2. When you're going to look at some of those alkenes and like our alkynes, those are going to be between 2 and 3, and so on. And or not alkenes, these are ketones, these hydrogens next to ketones. You'll see them between 2 and 3. Alkenes will be between the space of 4 and 7, and so on. The ones that I like to really highlight are aromatics are between 7 and 8 parts per million. Aldehydes are between 8.5 and 10. And carboxylic acids are super deshielded. So they're over here between like 11 and 12. So those ones are really helpful, especially when you start seeing oxygens in your empirical formula. You start looking like, oh, where's my peak? Is it like super to the left? If not, it can be like an alcohol. You'll see like alcohols, that peak number is not helpful. Like you're going to see like, this is a really wide range. The one indicator that you might get for these is that there's only 1 hydrogen in that peak. And so like that can be a good indicator of like, oh, like if it's got an integral of 1, then it's probably like on an alcohol or something, or you know, a special circumstance. Typically you'll see hydrogens that are attached to carbons in groups of 2 or 3, right? And also let me know if like the slides aren't working for anyone or you can't hear me. I guess if you can't hear me, you can't do much, but feel free to text in the chat if something goes wrong. But yeah, let's see. And then like our third step is matching those signals to peaks. So you want to notice the number of hydrogens for each peak and look for planes of symmetry. So like, for example, if I see that I have like, oh wait, sorry, the wrong way. We're going to just scribble this out. If I have like my, let's say this is my NMR graph, and I have like a peak over here that's like 9, what that's going to tell me is that that's probably 3 groups of 3, right? So I'm going to think like, okay, I'm going to probably have some sort of tertiary structure. So something that looks like this next to some other carbons, right? So I'm going to say that these 3 are like all the same. So they're probably accounted for by that like 9 peak, right? So you're going to do the same, like if you see like 4H or 6H, those can also indicate like 3 groups of 2, 2 groups of 2, and so on. Also helps you count the number of unique peaks when you're like drawing out your molecule. This is a great way to check. So yeah, and you'll get a little bit of practice with this on our problem set. So we'll have that as well. Apologize, I think. Let me just close this window. Okay, and here we've got, and finally, it's good to look at splitting. So splitting is something that is, I know, very annoying for organic chemistry students, but it is one of the greatest things that we have to identify molecules. Essentially, what you can do using splitting is you can find out how many distinct neighboring hydrogens you have, how many neighbors of a certain type you have as well. So you use the n+1 rule. And so using this rule, you can find the number of neighboring hydrogens of a specific type. If you see complex splitting, that means that you have 2 chemically distinct neighbors, and then you can sort of find out a little bit about both. So it can tell you where exactly something is. Something to remember is that neighboring hydrogens can only be detected by splitting if they are no more than 3 bonds apart. So the way you count that, and this is something that often is a point of contention, is you're going to count starting like, say, let's see, we'll do what is already sort of highlighted. Like if I start at this hydrogen over here, hope you can see that. Let me use a pointer or something. Let's see, laser. Yeah, so if I start at this hydrogen over here, then I'm going to first count the bond between that hydrogen and the carbon it's attached to. So that's 1. After that, I'm going to go down from that carbon to the next carbon over. That's 2. And then from there, from that carbon to the next hydrogen. Now, I can't go all the way past that. So I can't go to like this, like carbon's hydrogens, right? You have to make sure you're counting to 3. A lot of the time people forget to count that first bond between hydrogen and carbon. Very important. Make sure that it's exactly 3 bonds and no more apart. And then also, but yeah. And then something else to remember is also that if you have a double bond, that means that hydrogen is now in a fixed position. So as you see on this image on the right, you're going to see that even though these hydrogens look like, like they're vaguely similar, they're on an alkene, like they're all going to be very different. The position matters a lot. So even if like, say there was like a different, I lost my cursor. If I had like a hydrogen, right, instead of that, it essentially just means that, yeah, all of these hydrogens are distinct. You have to check for symmetry again. You can't treat this like a single bond. But yeah, here. And let's look at, we've got some common alkane substituents. And this is just a great way to start like solidifying some of those patterns. I know it's difficult at times to like interpret an NMR, especially when, like you're just starting OChem 2 and like you've just gotten off of all of those mechanisms, and now like you have to look at spectroscopy again. That's crazy. But I promise there's a way. You get used to it. It takes some experience. It definitely helps. So yeah, some patterns that you can start looking out for though is you can have ethyl groups, for example. So you've got those 2 carbon, like a 2 carbon chain. So one of those carbons is going to have 3 hydrogens. One of those carbons is going to have 2 hydrogens, right? You can only have 3 hydrogens on a terminal carbon. So that's a really great thing to see. And then when you look at that, you're going to see that, like, for example, our carbon with 2 hydrogens, that peak is going to be split 4 ways, that n+1 rule, right? So if I have 3 neighbors, I'm going to do 3 + 1, 4. And then same thing, this signal with 3 has been split 3 ways, which means that it's got a neighbor with 2 hydrogens. So you can say, oh, these are linked together. Same thing, you can take a look at the isopropyl and terbutyl, but like, for example, I talked about the terbutyl briefly. If you see a 9 like that next on a singlet specifically, that means that this carbon here does not have a hydrogen, which is often the case. And, you know, like past that, like this hydrogen over here on that amine does not count. Too far away. So some things to start looking out for. It definitely gets easier with time. And then also same thing with benzenes. You're going to want to look at, first of all, it's great to look at degrees of unsaturation. If you see 4 or like 5 or 6, that typically means you should start thinking like, can I see a peak between 7 and 8? Because that would be a benzene. So something to also consider for benzene is that depending on where your substituents are, that can change the lines of symmetry of a certain molecule, right? So we can see either maybe you have like just like 2 substituents. There's a lot of different options. So first, like if you have like 2 different substituents next to each other, you're going to see that every single molecule is like every single hydrogen is unique. So you're going to see 4 signals. But then, like, say you have your substituents across from each other, you're going to see a line of symmetry form such that, well, y'all can see a bit of everything, but yeah, you're going to see a line of symmetry form between such that you can still sort of have 2 signals. There's still a bit of symmetry happening. And same thing if you've got 2 of the same substituent right next to each other, that can form a line of symmetry. Now, if you have 3 substituents, you can still have a line of symmetry depending on where they are. So like this structure, we have the 2 same substituents meta to each other, 1 apart, and then a different in the middle. But that can really affect it. You should also look out for other patterns. These are just some of the basic ones, but definitely looking at the number of peaks that you have between 7 and 8 can really give you a good grasp of where you're going to be putting your substituents and what that like molecule is going to look like, right? Yeah, and so here is CNMR. I will say, yeah, I apologize if it's a little blurry, but so CNMR is, in my opinion, quite similar to HNMR. You're going to just see that any range that you're doing in HNMR, you just multiply that range by 20 to find those CNMR values. The one thing that does change is that your carbons on your ketone and aldehyde are both going to be within the 190 to 220 range. So that's the one big difference. You're going to be looking at those ketone carbons as well. Previously, if you remember, in HNMR, you would find a ketone like way over here. No longer the case. Just because like they're both equally deshielded, we're no longer looking at the hydrogen, we're looking at the carbon. I also really like to use CNMRs to identify distinct carbons. Something that you'll notice is that there is no splitting in 13 carbon CNMR. That means that it's not always the most useful tool to figure out how to build a molecule, but it definitely does help you figure out how many carbons, what functional groups you want. So it's a great helper to using your HNMR. Right. Okay, now moving on. We're going to look at some alcohol reactions, right? So got a pterodactyl now. I'm very excited. Right. So when it comes to alcohol reactions, you have done a little bit with alcohols in the past. In OChem 1, for example, you did look at deprotonation of alcohols. And so you can do that using NaNH2 to create an alkoxide, metal hydrides, or reduction by like those like alkali metals like sodium. And so that can just help you form a great nucleotide. You also did learn how to form alcohols last semester. There were a multitude of ways that you may remember from both your alkene and alkyne reactions. We'll go over some of the basic ones. First one being hydrolysis of double bonds. When you're doing, that's your alkene reactions, you can use like mercury and water to create an alcohol in a Markov fashion, right? You can also do SN2 reactions to replace on like an alkyl halide to form like an OH group where the alkyl halide was, right? And then finally, yeah, and then we've got a couple more. So we have, you can reduce carbonyls, which we're going to see the flip side of that in a second. And also you can use nucleophilic attack by Grignard's reagents. So that's a really great way to take a carbonyl and reduce it using a Grignard's reagent, and while also adding like an extra hydrocarbon. Right. So now on to the new stuff. So weak versus strong oxidation. This is an important player. You're going to be seeing it a lot in the next like semester, like this entire semester. So really what there is to know is that you've got a certain set of weak oxidizing agents and strong oxidizing agents. So the difference, when you have a secondary alcohol, there's no difference, right? Strong or weak, you're going to go to a ketone. But when you have aldehyde or a primary alcohol, you're going to see that with a strong oxidizing agent, you're going to go all the way to a carboxylic acid. There's no stopping. However, sometimes we want to stop. We want to create an aldehyde, for example, from our primary alcohol. So how do we do that? We use weak oxidizing agents such as our Sworn reagent, which is DMSO. You can use, I don't entirely remember what DMP stands for, but it stands for something. It's a good weak oxidizing reagent, and you can also use PCC. Some strong oxidizing reagents, on the other hand, include bleach, which is your sodium chlorate, I don't know, NaOCl. You've also got CaMNO4, which is manganate. You've got your nitrate, you've got chromate, and something to also note, chromate specifically reacts in an acidic environment. Like to be a strong oxidizing agent, chromate must react in an acidic environment. I believe PCC is when you use chromate in a basic or neutral environment. So it'll be weak otherwise. So that's why you'll see, like, for example, here chromate has H2SO4 as its buddy to help make it a strong oxidizing agent. Right. And let's see. Also something to note, tertiary alcohols can never be oxidized. Remember, carbon can only have 4 bonds. Any more than that, something's going wrong. We're not about that life, okay? So we're not going to do that here. And then in addition to oxidation, you can also do a variety of things with alcohols, including forming alkyl halides. This can be a really useful way to sort of convert into something that is a better leaving group. It can help you start doing some of those SN2 reactions and all of that. And, oh no, my drawing got cut off, but that's okay. So we've got phosphorus halides, specifically PBr3, PCl3, and Pi3. Those can all perform SN2 reactions with your alcohol. And so what they're going to do is essentially just go in and invert that stereochemistry while replacing the alcohol with a halide group, right? And remember, SN2 reaction, that means that you will have no reaction for a tertiary alcohol, right? Your other option is you can use thionyl chloride or SOCl2 to form alkyl halides with no inversion of stereochemistry. This is closer to your SN1 reaction. So it's great for when you want to add a chlorine, but you don't want to invert that stereochemistry. Okay, and so let's talk about the Lucas test. This is also something that's incredibly important to just be able to find out what kind of alcohol you have, right? That can really help you figure out what kind of reactions you want to do to get to a certain place, right? So what you're going to find is that the rate of Lucas reagent reaction, that Lucas reagent reaction really matters. That if it's extremely slow, that means that you're going through an SN2 reaction, and because it's a primary alcohol, even though it's a primary alcohol, because this is, what is it? Yeah, so your primary alcohols tend to undergo the Lucas reagent reaction really slowly because remember, alcohol is a really bad leaving group, right? So even though we're having an SN2 substitution, which is traditionally faster than an SN1 reaction, it's going to take us a while to be able to make that change, right? But then when we go into secondary and tertiary alcohols, we can suddenly start using SN1 reactions because that is preferred now, right? So that means our zinc chloride can really quickly deprotonate that alcohol and then make this into a really good leaving group, allowing us to sub in HCl, like adding in that chloride, right? So because basically we're going to convert our secondary and tertiary alcohol into a nucleophile with that zinc chloride. And then from there on, we can do that reaction, right? So that's why now we're looking at a reaction where we're making it a lot easier to use that alcohol versus having a leaving group that really doesn't want to leave, right? So that's why you're going to see tertiary and secondary really fast, primary super duper slow. It's going to take like over 10 minutes for this reaction to happen. Okay. Let's see. So another way that we can also create, because we talked earlier about forming alkyl halides, another way that we can convert an alcohol into a good leaving group is we can use tosylates. So you don't really have to memorize the structure here, but what you do need to know is that you want to react your alcohol, your like secondary alcohol with like, or primary alcohol with tosyl chloride, which is TSCl, right? To add that on, it suddenly makes alcohol into a great leaving group, OTS. This tells you I am ready for an SN2 reaction, right? So that's great. On the flip side, you can also use protecting groups, right? So you can use either TMS or TIPS to protect your alcohol groups so that other functional groups can react. This is a great way to prevent like reactions that we don't want to happen. For example, you'll remember with a Grignard's reagent, you can't react a Grignard's reagent in an acidic environment. However, if I put TMS on my alcohol, suddenly it's no longer acidic. So I can start doing my Grignard's reagent reaction without worrying about an alcohol, right? So always a great feeling, right? And something to remember, you're going to, in order to take off those protecting groups, you're going to want to use some sort of anion. Oftentimes, like fluoride is really great. Halogens in general are really great for that with water, right? So it's not too hard to take off either. Okay, so now we're on to carbonyl reactions. We've figured out how to make those carbonyls through our weak and strong oxidation. So let's see what we can do with those aldehydes and ketones now, right? So first things first, you can, hydration reactions control a lot of what we do when we talk about like carbonyl reactions. So there's two ways that these can work. You don't necessarily need to memorize them, but like I do like to keep them both up. You can have either base catalyzed reactions or acid catalyzed reactions. This is going to become even more important as you go into the next chapter and talk about carboxylic acid derivatives. Essentially, in a base catalyzed reaction, you're going to see a nucleophilic attack by your hydroxide at your electrophilic carbon, right? And it's going to attach. You're going to see that hydrate form, right, where you have saturated that carbon essentially with 4 different single bonds. And yeah, after that, you can protonate that to form an alcohol. So you're going to have see this one has 2 alcohols on that carbon. The other way is you can do it acid catalyzed. That's going to take a couple more steps. With a base catalyzed reaction, it's a bit faster because you're just using that hydroxide as a nucleophilic attack. Here, you're going to have to first protonate that carbonyl with an acid catalyzed reaction. After that, you can use a nucleophilic attack by water. to do something similar to before. And then, yeah, same deal here. Instead of protonation, you're going to deprotonate that water that has been attached. Right. So, but in the general gist of things is that you're going to see something that comes out looking like, let's see, we have our carbon in the middle, we've got 2 R groups, and then we've added on. We have 2 OHs now, right? And we're ready to rock and roll. Okay. In addition to that, you can also do you can create cyanohydrins. It's the same mechanism, but instead of having an OH group, you're going to add on a cyanide group. So you're just going to come in, you're going to attack as a nucleophile. It's going to, well, actually, it's your carbon. It's going to attack that carbon, and you're going to attach. Right. And same process, you're going to deprotonate that hydrogen, will come off so that you're just left with cyanide. But yeah, also a fun reaction to have in there, right? And then in addition to that, we have acetals and ketals, right? Or acetyls and ketols, whatever you want to call them. And so essentially what these do is they function as protecting groups. You can use those acetyls and ketols, acetals and ketals, I'll stop saying that, to prevent like either your aldehyde or ketone from reacting. So something to also remember and note is that aldehydes are more reactive than ketones. As you remember from HNMR, aldehydes also tend to be extremely de-shielded. That's because they have resonance structures, but in addition to that, our hydrogen is sort of a little bit easier to reach, right? If you were to draw it out, your hydrogen's right here, just for the taking. But essentially, what you're going to do is that, yeah, so you're going to react with some sort of diol in order to, you're going to react a diol with your carbonyl, creating oftentimes a cyclic acetyl or a ketyl. And again, this is also a great way to get into those Grignard's reactions where you want only one piece to react. Specifically, oftentimes, if you want to protect your aldehyde groups and go for your ketone groups. If you use just one equivalent, that is a great option, right? And same deal, you can just take them off with H+ and H2O. Okay, and then we also have imines and enamines. You might see a little bit more of this in the next unit as well. But imines are just carbon-nitrogen, like carbon double bond nitrogens. What you're going to do for that is you're going to react that with an amine to form that new double bond. And same thing, enamines are slightly different. When you do that, you're going to use tautomerization, which you might remember a little bit from last semester, where you're going to push that double bond. You're going to have 2 states where you can have your nitrogen double bonded, or you can push that double bond such that it's on the next carbon over, right? So these are 2 different states. And so this is specifically when you have a secondary amine, though. That's how you can do it, simply because you'll notice that this nitrogen here, it wants to only have 3 bonds. And so if we add a double bond into the mix, that nitrogen is not going to be happy anymore. So that's why we pushed that double bond over one, right? Okay. And moving on, we've got carbonyl reactions part 2, esters. I really like esters, so we're going to have a good time. If anyone likes perfume, esters are often, I believe, the thing that will help give them that scent. So, you know, fun facts in OChem. Yeah, so let's see. We've got Fischer esterification. That is one of our first reaction mechanisms. It's a great reaction mechanism simply because I really like it, because you can just switch out. You can create an ester out of any carboxylic acid. You're just going to do a nucleophilic attack by an alcohol. And what it'll do is it's going to do that exact reaction we were talking about earlier. This is an acid catalyzed hydration reaction almost. We're going to attack at that electrophilic point. We're going to attach on another alcohol, essentially right here, and that we can also just attach on whatever was attached to that alcohol, right? So we're going to add like the carbon chain. And then once you protonate that alcohol, you can have it turn into water, it leaves again, and then now, bada bing, bada boom, you've got ester instead of a carboxylic acid. So really great way to just sort of get rid of things, make something new, right? Transesterification works much of the same way. Now you're just attacking a different ester. You're going to go in and essentially you're going to take that group that's attached to the alkoxy group, that oxygen and like carbon chain, and you're going to replace it with our new, like whatever's on the alcohol, we're going to put over there, and that's going to be our new alkoxy group, right? So we're going to replace that R group, essentially. Pretty nice reaction. It's a really nice way to just add on carbons, decide on what you want. So I recommend using it in your synthesis reactions. And then finally, we also have hydrolysis of these esters. So again, you can have base catalyzed or acid catalyzed reactions. Both end similarly, but just something to remember. It's a good way to know that there's two ways to do things. But yeah, both of them end with just forming that carboxylic acid that we began with, right? And an alcohol. So you're converting your ester to a carboxylic acid, right? And that really does conclude all of our information for the night. I'm going to say thank you to a number of people, Dr. Novak, and then these are some of the people who helped put together previous exam reviews for the same exam, Police, Zero, and Tyler, so for their contributions to the materials. And now, okay, I know it says good luck on your exam, but we have a second part to this. We're going to be splitting up into groups so that we can work on some problems. We've put together a bit of a problem set for you tonight so that you can take a look at some questions, try to apply the concepts that we talked about, and just make sure that you're ready for that exam. So if you want to stick around for that, feel free. If you need to leave, we understand that it's late. Some people have dinner plans, but where do you want to get started?
I would like to start with the synthesis because I feel like that's pretty important. So we will just start on number 1. Do you want to have the students like work on the paper, or like have me just like work through the problems myself and explain it?
So what we typically do is I like to give people a chance to look at those questions, and then after everyone's tried one. So given that we have 4 people and 4 questions, okay, letter D, okay, is not a synthesis. So what we can do is we can have one person, like 2 people double up on one of these questions. So like Abigail, if you would be willing, could you do A? It just says guest, but whoever's guest, could you do B? And then NK and Cheryl George, or Cheryl, can you do C? But yeah, sorry. Mostly it's just nice to have people try them out, and then we can have everyone explain. Because you're a PLTL leader, right?
Yes, or CHEM.
So however that session looks like for you, it's mostly something like that for us. It's pure tutoring.
Yeah, so guys, go ahead and write on the board, on the document, and if you need help, just unmute or feel free to type your question in the chat, and then we'll go over them all together. I'll give you guys until maybe like 7:50. Okay, let's go ahead and get started. Abigail, are you there? I won't make you do it yourself. You can be like my scribe for the first one, but can you hear me?
She might be having some trouble with the internet.
Okay. Should I just go ahead and like work through it?
Sure, we can do that.
Okay. Sounds good. So, if you guys can see, we start off with an alkane, with an alkene double bond in the middle, and then we're going to a tertiary alcohol. What I always like to do when I'm given a problem like this, where I have to come up with the steps in between, I like to count my carbons. I think that really helps put into perspective what is going on in the problem. Let me figure out how to write on this. Okay, so we have like 1, 2, 3, that's really good. 4, 5, 6 carbons, and then here we have 1, 2, 3, 4, 5, 6, 7. So somewhere along the line, we're going to be adding a carbon. So we'll keep that in mind. If you guys remember, one of the reactions that we can use in order to remove that double bond and add an OH group is called alkoxymercuration demercuration. So we will go ahead and work that out. Give me just 1 second. Okay. So with alkoxymercuration demercuration, you're going to be using a reagent called HgOAC2 with water and NaBH4. So I'm going to go ahead and draw that out. And then you're going to use water. And then your second step would be NaBH4, which we know is a reducing agent. And what this is going to do is it's going to add water across the double bond. It doesn't really matter for this problem, but usually with this reaction, the OH is going to add to the more substituted side. So this is going to be a Markovnikov addition of water to the double bond. So on one side of the double bond, you're going to have an OH, and the other side you're going to have a hydrogen, which makes up H2O. Then we're still trying to get to a tertiary alcohol, and right now we're only at a secondary. So if you guys remember, we can do an oxidation and then a Grignard reagent in order to make that secondary alcohol go to a tertiary alcohol. So I'll go ahead and draw that out. And when you have a secondary alcohol, it doesn't matter if you use a strong or a weak oxidizing agent, because the product is going to be a ketone regardless. So you can use PCC, you can use Swern, any of the chromate reagents, the chromic acid reagents, in order to do that oxidation. And then we have to add a Grignard reagent. And if you look, the only group that we're really adding is this methyl right there. So all you have to add is a CH3 MgBr, and then that will give you your final product. Does anyone have questions on that, or can I move on? Okay. Grignards are really great for adding carbons. So keep that in mind, and counting carbons really helps with that as well. All right, let's go ahead to part B. Cheryl, are you there? Would you like to help me on this one? Okay. Let's go ahead and work this one out. So if you can see, we're starting with this structure right here. It contains a primary alcohol, it contains a ring, and also an alkene double bond. And what we're trying to do here is essentially we're just removing this double bond and adding this carbonyl group right here. So let's first look at the substitutions across the double bond to see if we need to do a Markovnikov or anti-Markovnikov addition. Okay, so this carbon of the double bond would be more substituted than this carbon. And we're trying to add the double bond to the less substituted carbon. So keeping that in mind, we know that we're going to have to do an oxidation at some point. But if you can see, this primary alcohol right here stays. So we need to do something in order to protect that alcohol. And the reagent you can use for that is TMSCl or TIPSCl. So let's go ahead and draw that out. I'm going to say our first step is to use TMSCl, which is an alcohol protecting group. And then when you write it out, you abbreviate it as TMSO. And you can draw the rest of your structure. Excuse my hexagon drawing. Okay. From there, what we're going to have to try to do is add water across this double bond so that we can eventually get to this ketone right here. And if you remember, like I said, we're going to be adding the OH to the less substituted side of the double bond in order to get this product right here. So that would be an anti-Markovnikov addition of water, which means that the OH is going to go on the less substituted side. And the reagent that does that is your step one is going to be to add BH3 with THF. And your second step would just be hydrogen peroxide with a base. And what that does is it just hydrolyzes the double bond, and it's going to add OH to the less substituted side. So if we redraw the structure, the alcohol protecting group stays there. We're not doing anything to that yet. You can redraw the ring, but this time we're going to remove the double bond and add the water. And then this would be an H right here that we added to make H2O. So as you can see, we're already almost there. We just have to oxidize this into a carbonyl and get rid of this alcohol protecting group. So what we're going to do first is oxidize the primary alcohol. And we can do that using pretty much any oxidizing reagent. I'll just use PCC. And then after that, we can remove the TMS group. And then we can use a fluoride anion for that. So that would get us to our final product. Okay. I'll go ahead and erase this. Or actually, I'll leave it up for now. Moving on to the next problem. We can see that we are getting rid of an alcohol and adding some carbons. So if we count our carbons, we have 1, 2, 3, 4, 5 in the first structure, and then we're going to 1, 2, 3, 4, 5, 6, 7 carbons in the final structure. So we know somewhere along the line that we're going to have to add 2 carbons. Choose a different color. Okay. So one way we can do this is by creating an aldehyde first, which would then allow us to use a Grignard reagent to add those carbons. And we know that we can oxidize a primary alcohol to an aldehyde with a weak oxidizing agent. So let's go ahead and draw that. And then we can use, let's just say PCC. Then what we can do is we can add a Grignard reagent in order to turn that aldehyde into a secondary alcohol. So let's use CH3 MgBr. What that's going to do is it's going to make an alcohol right here. And then it's going to add this CH3 group. The hydrogen is still there, we're just not drawing it. But what that does is it gives us that extra carbon. So now we just need to add 1 more carbon somehow. We could think about doing a substitution, but the thing is that OH is a pretty poor leaving group. So what we can do first is make it an alkyl halide with PBr3, PCl3, something like that. And what that's going to do is just substitute the OH with the Br. And now we know that Br is a good leaving group. So what we can do now is we can use what's called a Gilman reagent. This is an organochute, so you're just going to use the R group attached to CuLi, or copper lithium. So the way you would do that is, all we need to add now is a CH3. So we do CH3CuLi. But what you have to remember is that you need to have 2 R groups with the organocuprate reagent. It's only going to add once, but you just have to write it that way. So just think of it as writing R2CuLi. And then that would bring us to our final product. Essentially just doing an SN2 reaction. So you can see that we added a carbon over here with the Grignard, and we added another carbon over here with the Gilman reagent. That would bring us from 5 carbons to 7 carbons. Okay, feel free to drop any questions in the chat if you are confused or need me to cover anything again. But moving on, we're given a Fischer projection here, and we're asked to react it with HNO3, water, and heat. If you guys remember from Ria K's presentation, HNO3 is a strong oxidizing agent. So let's look at the structures we have here so far. Here we have an aldehyde. here we have alcohols. More specifically, they would be secondary alcohols. And then here you have a primary alcohol. So, knowing what we know about strong oxidizing agents, they're going to oxidize primary alcohols and aldehydes to carboxylic acids. And they will also oxidize secondary alcohols to ketones. So basically you would just redraw this structure, keeping in mind that this right here, this aldehyde here, will turn into a carboxylic acid. And this primary alcohol right here is also going to turn into a carboxylic acid. If we partially react it with HNO3, these structures here would be fine to be drawn as secondary alcohols. But if you go all the way, they would turn into ketones. So Ria, can you fact check me on that? Do I just draw an O here, like for the ketone, or do you just want me to draw it as the alcohol?
Sorry, could you repeat that for me?
Do you want me to draw all the middle atoms with just the oxygen for the ketone?
Yeah, or? We'll just do a double bond for that oxygen. We're going to take off that hydrogen bond as well then. So we can also draw that out like normally if you'd like. Mostly we just wanted to notice that like you're going to be changing all of those alcohols right, as well as the carbonyl.
This is not.
Mm-hmm. So if you do just want to say like we're going to turn all of these into like carbonyls, yeah, like ketones, that's okay.
We'll just do that.
Yeah.
I can get my computer to work. Okay. So then you're going to have 4 ketones here.
Mm-hmm.
Awesome. Yeah, those are some of our synthesis reactions.
Mm-hmm.
The recurring themes that you guys can probably see here are a lot of oxidations, and then also adding carbons by using Gilman reagents or Grignard reagents. So if there's no questions, we will move on.
Yeah, and we can choose what questions we want to cover. You don't have to cover all of them. But if anyone has anything in specific that you want to see,
yeah, Abigail and Abigail and NK, if you guys have anything in specific, just unmute or drop it in the chat, and we will skip to those questions. Let me see.
But yeah, we've got some ranking questions. We've got some NMR questions, mechanisming, reaction questions as well. And like, I mean, any questions we have can be gone over, so.
Yes. Would we have ranking on the exam?
So I can't speak on that. Ria, you may know. But
I haven't.
Yeah.
Okay. I feel like Novak does like his ranking though.
Mm-hmm.
Yeah, I would ask your professor that.
Yeah.
Like
yeah, it's always good to have a basis in those questions because downfield shift, figuring out the number of signals, those are all things that you will need to know how to do. Also, don't worry about like if we don't get to all of those questions. you can, of course, we're going to be uploading the answer key as well, and I can drop that link in the chat. So we'll have some things. But yeah.
Ria, is that you doing that?
That's not me. So.
Oh, okay.
Through them, let us know.
Just so you guys know, if you click the arrow, it will move for everyone.
Yeah.
Okay. So I guess we can do a ranking question just in case. Let's start off with an easier one, I think. Number 4 says to rank by the number of signals on a CNMR spectrum. The compound with the most signals is 1 and the least is 5. So what we know about CNMR spectra is that you're going to be looking for symmetry, and you can figure out the number of signals with that. So if we can start drawing planes of symmetry, you guys are welcome to draw on the paper as well. I will get us started. Okay. For this first structure right here, we have a plane of symmetry there. We have a plane of symmetry here. So all of these hydrogens and carbons are pretty much going to be the same. So you're only going to have one signal. We'll write that up here. 1. For NO2, we have a plane of symmetry going right down the middle. So that's going to give us 1, 2, 3 carbons on either side. So that would give us 3 signals. We have 3 distinct carbons. With this one, we don't have any planes of symmetry because this NO2 is kind of in a weird spot. So each carbon is going to be chemically distinct, giving us 4 signals because we don't have any planes of symmetry. This one might be a little hard to tell at first, but you actually do have a plane of symmetry going right here. So that's going to give us 1, 2, 3, 4, 5, 6 chemically distinct carbons, or chemically distinct, 6 different signals, essentially. And here we have a lot of symmetry going on, so we can draw it this way. You have your 2 planes of symmetry here. So the only carbons that are really going to be distinct are 2 of them in any plane that you choose. So there you have 2 signals. So now it's asking us to rank the compound with the most signals as 1 and the least signals as 5. So just doing that really quick. The most would be the 6 here. So that's first. This one would be second. This one would be third, fourth. And here we only had 1 signal, so that would be last. Are there any questions about that? Or was that pretty easy?
Yeah, and like feel free to ask anything, like it's okay.
Yeah. Okay. Let's do number 3 then. It says to rank by downfield shift in HNMR. Each compound will have multiple signals, but rank it by their most downfield peak. The molecule with the peak furthest downfield will be 1 and the least downfield 5. So kind of going back over what Ria K covered in the review, downfield means basically de-shielded. De-shielded. And then that would be more like left on the chart. Okay, so let's go ahead and pick out our hydrogens. We only have really one option here. We have hydrogen there. You have some hydrogens here on the double bond. And then this one would be more downfield as well. And then you can use this hydrogen. So when you have more electrons surrounding your protons, you're going to have more shielding. So the most shielded would be this silicon structure right here, because you have all of these protons, all these hydrogens coming off. So that would be your most shielded. Hold on, I got the number wrong. Your most shielded, meaning it would be 5. After that, we know that resonance and double bonds increase the shift downfield. So the more double bonds you have in your structure, the more resonance, the more downfield your shift is going to be. So our options here are this structure, and this aldehyde structure right here. So your carbonyls are going to be the furthest downfield. So that would give you 1. And then after that, we're in between these third and fourth structures right here. So at this point, we have pretty much the same exact structure, except the groups NO2 and I are different. So we're going to have to look at the electron withdrawing abilities of NO2 and I. So NO2 is going to be more electron withdrawing than iodine. So this would be the next most downfield. And then iodine would be right after that. And then this one would be 4th because we don't have any double bonds that are increasing that shift downfield. If that doesn't make sense, if any part of that doesn't make sense, feel free to drop your questions in the chat. Or Ria, Kay, if there's anything you'd like to add that I missed.
I think that was pretty good. Yeah. And I'd say like we can take a look at some other questions, but yeah, like if we don't have anything in specific, we're just going to be going around. But like, again,
okay.
Yeah.
I think there were some pretty good synthesis questions at the end of the.
Yeah.
The end of it. Do you want to go ahead with synthesis or do some NMR?
I would say, okay, let's do like one of these NMR questions, and then after that we can look at some synthesis, just so we can have a little bit of that on record as well.
Awesome. Okay, we can go ahead and do this first one. So like Ria said, the first thing you should do when you look at an NMR spectra like this is to count your degrees of unsaturation. So we have our formula given right here, and so we're going to do 2 times the number of carbons, which is 7, plus 2, minus the number of hydrogens, which is 5. We also have a Cl, which counts as X. So we would do minus 1 there as well. All of that over 2 gives us 5 degrees of unsaturation. So like Ria said, one of the most obvious ones, I guess, is 4 degrees of unsaturation gives you a benzene ring. So we can go ahead and start with the idea that we have a benzene and maybe some other double bond. Okay. If you look at our chart, oops, we only have 3 distinct signals. So that could probably tell us something about the symmetry that's going to be present in our structure. Okay, so going ahead with drawing the structure, we could start out with drawing a benzene ring and seeing where everything else fits from there. If you look at the chemical shifts, that also matches up with the benzene shift. Okay. So that takes care of 4 of our degrees of unsaturation. The other thing we have to do is figure out where that the 5th degree of unsaturation goes. And in our structure so far, we have 6 carbons and we have just lost my train of thought. Okay, we have 6 carbons so far in our structure, so we need to account for 1 more carbon. So we know that there's going to be some planes of symmetry here. So let's try to put the Cl on one of the carbons and see where to go from there. Okay, so now this signal right here corresponds to an aldehyde. You know that because it's pretty far downfield, and the 1 singlet will correspond to an aldehyde signal. So we have a bunch of these carbons that we could put it next to. But in order to get that symmetry, it's going to be right in line with the Cl here. So if we draw it out, this might be the best place to put our aldehyde. So if we count our carbons, we have 1, 2, 3, 4, 5, 6, 7. If we count our hydrogens, we have 1, 2, 3, 1, 2, 3, 4, 5, and then we have our Cl. So that would be your final structure.
Okay. Yeah. And yeah, fun exercise is always to just go back and check what hydrogens are where. So always that. Looks like we're left with a single student though. NK, do you have any specific things that you want to look at? You have the world in front of you. Otherwise, while you're here, we can look at maybe one of those synthesis problems and close it out for the night.
Sounds good. We can do one of the last few. Those cover a good amount.
That was the hope.
I think number 10 is a good one.
Yeah.
Okay. So this one says to follow the sequence of reactions and determine if the product shown will form. If not, explain why. So if they give you a question like this on the test, I would honestly go ahead and draw out each step of the synthesis so that you're not doing it in your head. So let's go ahead and do that. Okay, So we're given a primary alcohol. I also like to go ahead and like label things that I'm given in the problem, just to keep my head on straight. So we're given a primary alcohol reacting with PBr3. So we know when that happens is we get an alkyl halide. So our first step would give us the same structure, but you're just essentially substituting the Br with the OH. And that works out perfectly for our next reaction, which is a Grignard formation. So you get this little alkane with an MgBr at the end. Okay, here we are given an aldehyde in an acidic solution. So this is going to react with the Grignard reagent in order to give us some sort of an alcohol. And this will be a primary alcohol because if you look here, we have no carbons on these R groups. Both of these R groups are H's. So when you add the alkane from the MgBr, you're going to get a primary alcohol again. So basically, the MgBr is going to attach itself like right there. And then it's going to kick up the double bond and form an alcohol. So if we redraw that, we're basically just extending the chain by one carbon. So now we have another primary alcohol, and we are given this Na2Cr2O7. We know that this is a strong oxidizing agent because it uses chromium, and all of our chromium reagents are going to be strong. And we've seen time and time again that when you're given a primary alcohol with a strong oxidizing agent, it's going to oxidize past the aldehyde and go to the carboxylic acid. So this structure would be incorrect. If we redraw it correctly, you're going to go all the way to the carboxylic acid. So this step would be incorrect in the problem. If you did want to stop at the aldehyde, you can use any of your weak oxidizing agents, such as PCC, Swern, things like that. So what we've done in this problem is carbon. We've added a carbon chain. Oh, sorry. We've added a carbon chain with the Grignard reagent, and we have done an oxidation with a strong oxidizing agent. Awesome. Rhea, do you want to do one more, or should we stop it there?
Yeah.
Or anything else we can ask you.
Yeah. If you have any specific questions, we can look at those NK. Otherwise, I'd say it's a good stopping point. All of these questions will be posted on the YouTube channel. So if anyone who's watching not live wants to take a look at those, please do. You can always come by peer tutoring, or if you're in PLTL, you can come by and ask someone about those questions for clarification. But yeah. Do you have anything you want to look at, NK? Okay. I'm going to say let's just close out the session. It is 8:30. Oh, yeah. Okay. Have you been able to hear us, or is there anything you want us to see? I'm sorry that your audio has been cutting out. Okay. So I can actually put those in right now. I don't have the official ones that are going to be posted, but these are the ones I made. So if you want to look at them, I do have a link. Here, let me just find the sharing link for that, and I can send that in the chat. Yeah. And if you have any specific questions, feel free to come by and ask them. But yeah, if you take that link, it'll take you to the questions as well as the solutions and that PowerPoint. If you do also want to see them online, they'll be in the description of our YouTube video that we'll be posting. Yeah. But thank you for coming. I'm going to stop the recording now.